Hey everyone, we're going to be finishing up our chapter 6 today. So this is chapter 6.3, day 4, 4 days of chapter 6.3. That's quite a lot. So this is a game called Greed. Let's check it out. Okay, we're going to play Greed. Every round you must decide if you want to sit or stand. If you sit, you'll keep all the points that you've earned, but you are no longer playing. In other words, you can't stand up again. If you choose to stand, you must play for the round. You're going to earn 1 point for every round that you make it through. What's going to happen is Mr. Ferreria is going to roll a die, and if the die lands on a number between 1 and 5, everyone who is standing will move on to the next round. In other words, they will earn a point. And if the die lands on a 6, every person standing will lose all of their points. So let's pretend, I've made it 5 rounds and I'm still standing on the 6th round, and that's when Mr. Ferreria rolls a 6. That means I actually get 0 points. So it's either all or nothing. And we've played this game before in other semesters. Probably in future semesters we'll be playing this too. But unfortunately, if you're doing this here at home, we can't really play this game. So we're going to have to just look at this theoretically. So theoretically, number 1, how many points did you earn? Well, let's just theoretically say I earned 4 points. Let X be the number of rounds played until a 6 occurs. Is this a binomial setting? Well, we can go through all of bins to see if this is binary. We can go through all of bins to see if this is a binomial setting. So is this binary? Well, the outcomes are either 6 or not a 6, so that looks pretty binary to me. Is it independent? Well, we're talking about dice, and dice rolls are independent, so we qualify there too. N. Is there a set number of trials? And no, there is not a set number of trials. We're just going to keep playing until I roll a 6. So since we have stopped here, this is not a binomial setting. Greed is not a binomial setting. But that doesn't mean that we're hosed on this one. We can still do a lot of things. So firstly, we can use probability rules to calculate all of this. Okay, so let's figure out what's the probability that x equals 1. That means we roll the dice 1 time and we got a 6. What's the probability that x is 1? It's not that bad actually, because we know that we're going to roll a 6. And the probability of rolling a 6 is 1/6. What about the probability that x equals 2? Well, let's think about what's going to happen. The first thing that has to happen is we need to roll something that's not a 6, so anything but a 6. And then on the second roll, we have to roll a 6. So the probability that we roll anything but a 6 is 5/6 multiplied by the probability that we roll a 6. Which is 1/6. Now, what about playing the game 3 times? What has to happen? Well, we have to roll something other than a 6 on the first roll. We have to roll something other than a 6 on the second roll, and then we have to roll a 6. So that's a 5/6 times 5/6 times 1/6. Well, that's the same thing as 5/6 squared multiplied by 1/6. Next case, what happens if we want to play this game 4 times? Well, we have to anything but a 6 multiplied by anything but a 6 multiplied by anything but a 6 multiplied by a 6. So what does that look like? All right, that's 5/6 cubed multiplied by 1/6. Now you probably noticed that I made that exponent in a different color. And that's kind of the key to figuring out what's going on with these probabilities. Now, what do we relate that to? Let's examine the pattern. Here, when x equals 2, we multiply 5/6 to the first power multiplied by 1/6. When x was 3, we multiplied 5/6 squared multiplied by 1/6. And when x equals 4, we multiplied by 5/6 to the third power multiplied by 1/6. So do we see the pattern here? This power has to be one less than whatever number we're calculating. So if we want to calculate a general number such as k, we've got to do 5/6 to the k minus 1 power multiplied by 1/6. And that's really our formula. We have figured this out. So write the probability that a 6 is rolled within the first four. Actually, before we do that, let's just talk about what we're looking at here with number 3. This kind of distribution is called a geometric distribution. Now, a geometric distribution is almost just like a binomial distribution with the glaring, well, let's just go over all the conditions. The first two conditions are just like the binomial distribution. We have binary outcomes again, and independent outcomes, so the probabilities of past events don't affect the probability in future events. But what makes the geometric distribution is that we're interested in how many trials until the first success. Okay. And then just like the binary the binomial distribution, it's the same probability for each trial. So the only thing that really changes here is instead of the set number of trials, we just keep doing this until we get at a success, just like we did for greed. Now, for number 4, we're supposed to write the probability that a 6 is rolled within the first 4 rolls in terms of x. So find that probability. Well, the things that could happen is that you could get the first success in the first roll, or you could get a success in the second roll, or you could get the first success in the third roll of the dice, or you can get the first success in the fourth roll of the die. Now, if you're looking at this, you're probably thinking, yeah, that's a lot of calculations. I mean, I did all the calculations up here with A, B, C, and D, but if this was only question, that's a lot of things to do. Well, luckily for us, there is a calculator command that does exactly this. And that is the geometric CDF. So let's take a look at our calculator. We're going to go to second distribution, and we're going to go past, actually we're going to go the other way around, and we see a geometric PDF and a geometric CDF. Now the distinction between the two is that if you want to know the probability that x is exactly equal to a number, you're going to use PDF. And if you want to know the probability that x is less than or equal to a number, that's when you're going to use geometric CDF. Back here at the calculator, we're going to do geometric CDF. P is 1/6. You can type a 1/6, that's fine. And the first, we want to know sometime in the first 4 successes, and that will give me a result of 0.5177. For number 5, we're going to ask how many rolls would you predict until it would take until a 6 is rolled. And for that one, we're going to do some calculator mischief as well. For L1, I've gone ahead and I've put the numbers from 1 to 20. And in L2 here, I'm going to scroll up and highlight L2. We're going to put a geometric PDF where the x values are all in L1. So let's paste that on here. So L2 is a geometric PDF. Probability of success is 1/6. And the x value is going to be in L1. And that'll really quickly give us all of those outcomes. Okay, so now that we've done that, let's go ahead and make a histogram of this geometric CDF. So second stat plot, geometric PDF. We want a histogram, of course. L1 is going to be our list. L2 is going to be our frequency. Okay. And now we're going to go ahead and go to Window. Negative 0.5, and I went to 20, so I'm going to make this 20.5. We want each bar to be 1 across. And if I remember correctly, the maximum was definitely less than 0.5. I think we could put a 0.3 here, and that'll look good. And we're going to go from, negative 0.1 to positive 0.3. Let's graph it and see what that looks like. Yeah, there we go. So here's how you would go ahead and make some kind of a geometric PDF. This would be the histogram of the PDF. Yeah, this is a pretty good skill. But that doesn't really tell us how many rolls would you predict until a sixth is rolled. And, the answer here is 6 rolls. And we would say 6 rolls because P is equal to 1/6. Now, this brings us to what we would call the mean. The mean of a geometric distribution is 1 over P, which in our case was 1 over 1/6, which is equal to 6. So that kind of vindicates or explains a little bit about how we got 6, even though we didn't know this rule yet. So this is the correct way to find the mean of a geometric distribution. How about the shape? What do you think the shape of this distribution would be? Well, actually, we saw the shape. The shape is a right-skewed distribution. And so the shape of any geometric distribution is right-skewed, and that is always. And this brings us to our important ideas for geometric distributions. All of these things we've already talked about in our geometric distribution discussions. We know that the conditions for a geometric distribution is bits, binary, independent, trials until success, and same number of probability for each trial. We just saw that the mean is mu, 1 over p, and the shape is always right skewed. Additionally, we have calculator notation. So for the calculator, if you want to know the probability that x is equal to some number, then that is a geometric PDF. And if you want to know the probability x is less than or equal to a number, that's a geometric CDF. Let's check our understanding. Marty decides to keep placing a $1 bet on the number 15 in consecutive spins of a roulette wheel until she wins. On any spin, there's a 1 in 38 chance that the ball will land on the 15 slot. So show that t is a geometric random variable. This means bits. First of all, is this binary? Yes. Either the ball lands on 15 or it doesn't land on 15. How about independent? Yes, again, past outcomes do not affect the future outcomes. For the trials here, we're going to keep playing until we get a 15. And finally, do we have the same probability of success? And yes, p is 1 over 38. Next, let's find the probability that t is equal to 3, and let's interpret that result. Now, you might be tempted to just go ahead and use geometric PDF here because that would be appropriate. But in my head, there's almost no reason to use it since this calculation is so easy and you get so much out of it if you think of it in these terms. So the probability that t is 3 is 37 out of 38 squared for the 2 failures and 1 out of 38 for the 1 success at the very end. So 0.0249, there is a 2.49% probability that Marty wins at roulette on her third game. How many spins do you expect it to take before Marty wins? Well, that's asking for the mean. So the mean, which is the same thing as expectation, is 1 over 38, which is 38. So we would expect Marty to win on her 38th game. Would you be surprised if Marty won in 3 or fewer spins? Compute an appropriate probability to support your answer. We're being asked to find the probability that the number of games until the first win is less than 3. That's the binomial CDF, P equals 1 over 38 and X equals 3. I mean the geometric CDF, where P is 1/38 and X is 3. And that's about 7.69%. So the probability is low, but we wouldn't be surprised since the probability of winning in the first 3 games is 7.69%, which is, and if you remember this, it's not rare because it's greater than 5%. Rare is less than 5%. So we would not be surprised. So that takes care of everything we're doing here on geometric probabilities. This is the end of the chapter, so good luck on your test, and we'll see you next time.